Okay, so recall what we were doing. Let me just write down a few things to motivate what's going to be coming. So we've said that we want to generalize from this discrete index to a continuous index. Okay, so let's start to draw some parallels. So this equation over here that I've just underlined in red is the analog of this equation over here. And what you can see is I've got this function gi of t appearing. Now, remember that I has been replaced by t primed, so it should be identified with some function of t and t primed, and we said we can identify it with the delta function, okay? Good. And then the other thing is this equation, this is the one that we solve, is related to this equation, which is the one that we solve. And I want you to look at the right-hand side of these two equations. You can see that gi of t appears inside this equation, and inside this equation, delta of t minus t prime appears. Okay, so those are completely analogous, those equations. It also lets us see that what we're calling alpha I in this equation is actually what we call b of t primed inside this equation. Now, what is the solution? Well, the solution is the solution is, so we will have f of t equals this discrete sum over I is going to become an integral over dt primed. That's what a discrete sum becomes. It becomes a continuous integral. And then the alpha I of t of our previous problem has become b of t primed. So we'll have a b of t primed sitting over here. And then the gi of t, we said, is the gi of t becomes delta of t minus t primed, okay? But we solved this equation for the fi. So let's just, this is fi. Let's maybe outline it there. And fi becomes, in this problem, f of t comma t primed. Now, what you can notice is this equation that we're writing down over here is the analog of this equation. Why? These are both the solutions to the problem. We've got the sum, we've got the alpha I. The only thing we need is fi of t. And what is fi of t? Well, this is nothing but the f of t comma t prime. That's what we actually, that's the equation that we solved, okay? So I've written down this underlined green equation just by looking at the equation at the top and just by writing down the analogous thing. What else can we say? Well, we said that the solution is a linear superposition of the solutions that we found originally. And you can see that now our f of t is an integral dt prime, b of t prime, f of t minus t prime. But f of t minus t prime is the solution that we found before. So again, it's a linear combination of the solutions. So I hope that what you can see is, I hope I've convinced you that this box that I'm underlining now, this equation, I've obtained just by writing it down in analogy to the discrete problem. So I hope that you can see that analogy perfectly. If not, please think about it. But what I want to do now is I want to check that this really is a solution. So let's check this, okay? So we're going to take O hat acting on f of t is equal to. Now, remember before we always used linearity. So what did we say? We said that O acting on the sum of solutions is the sum of O acting on a sum of terms is the sum of O acting on each term. And it's the same thing here. O acting on a sum of terms or integral of terms is, so here we've got O acting on an integral of terms. And what is this equal to? Well, this is equal to the integral of O acting on each term. And let's just make sure that we're completely happy with this step. You know, what is O going to be? O is going to be some sort of a differential operator, so it will have derivatives in it with respect to t. So that's why it just goes straight through the t prime, straight through the b of t prime, and it acts only on f of t and t prime, okay? Because it's a derivative, it's got derivatives in it with respect to t. So it'll go straight through the integration measure, straight through the b of t prime. But now we know what O hat acting on f of t comma t prime is. That's just the delta function. So we'll have an integral dt primed, b of t primed, delta of t minus t prime. But you know how to do this integral over the delta. The delta is just going to set t prime equal to t. So we'll end up with b of t. So indeed, we have solved our differential equation. Now, what did we gain? Let me maybe just stress one thing that we'll talk about a few times. We solved this equation underlined in red. That was one equation to solve, and we got f of t and t primed, okay? Then we wanted to solve this equation that is in blue. Let's make it a blue box. So we want to solve this equation that was in the blue box, which is star. Now, that's an infinite number of different equations because there's a different equation for each function b of t. And what we've managed to do is we've managed to write down the solution in terms of b of t in this final box solution, and we only used the solution to the equation underlined in red, okay? Now, the notation that I've used is not great at all. So let's try to fix this up a little bit. So that f that I had at the beginning there, I'm going to call this g, okay? So maybe this is a better notation. Not maybe, it definitely is a better notation. So there I've changed G as well. And everywhere I see an F, I'm just going to change it to a G. So there we go. So now I've improved the notation just so that I didn't have F doing too much work, appearing too many times. And the other thing that's nice about this notation that I've adopted now is that this function G of t comma t primed, this is what is called the Green's function. Okay, so now you have seen exactly the Green's function method. I hope that you can argue it in the discrete problem. It's very easy using linearity. And then just by analogy, you get the solution for the continuous problem. Okay, good. Now let's come back to the problem that we wanted to solve originally. Okay, so let's apply it now to our problem. So this is the problem we wanted to solve. We had d mu plus m squared phi naught of x is equal to minus ij of x. So let's solve this using the Green's function method. So we introduced the Green's function. Now, what was the Green's function? It was our linear operator, O hat. For us, O hat is d mu plus m squared. So this is what O hat is. And then we acted on the Green's function. Now here, we haven't just got one variable. We've got x mu. So it's a time and three spatial positions. So our Green's function here will not be a function of t and t prime, but it will be a function of x and x prime. Let me call it x and y. And both x and y, they each are a time and a spatial position. And then we should set this equal to a delta function. This will be a four-dimensional delta of x minus y. If you write it down like that, that's perfectly good. One of the conventions that we have in quantum field theory, and it's just a convention, we include the minus I in front of the delta function. So I'm going to stick with that convention, but that's not a big change at all. And I want you to check that what we write down as a solution, I want you to check that that really is a solution, okay? So this first equation here is the analog of the equation that we had underlined in red. So let me underline this in red. The second equation, the one that we, oh, sorry, I shouldn't have said that because that wasn't true. The equation underlined in red is this equation. That's the Green's function equation, okay? So the equation underlined in red at the top there becomes the equation underlined in red over here. And the equation that we wanted to solve in the blue box, that becomes this equation over here. So now I just want to write down the solution. So what is the solution? Well, the solution would be the following. We would say phi naught of x, that's what we're solving for. Phi naught of x equals to, we have an integral. So now I'm looking at the equation underlined in green. We have an integral, d4. So t prime we've represented by y. Then we have b of t, and b of t is what appears inside this blue equation. So it would be minus ij of x, that's on the right-hand side. But in actual fact, the minus I we've already included inside the Green's function. So it's just j of y. And then look at the underlined green equation. We should have the Green's function g of x comma y. And this is the analog of the equation underlined in green. And I want you to check that this really is a solution. So I want you to check. This is a solution. And you see, the idea is quite simple. Take O hat, which you know is d mu plus m squared. If you act on phi naught of x, well, all of these derivatives with respect to x, so you can take them into the integral, and this operator is only going to act on the g of x comma y. When it acts on the g of x comma y, it's going to produce minus I delta 4x minus y, then use the delta function to do the integral over d4y, and you'll be able to verify that the equation underlined in blue is actually correct. So we've solved the equation underlined in blue for any arbitrary function j of x, but we've done that in terms of the Green's function. And the Green's function solves the equation in the red box. So our next task is going to be to solve for the Green's function by solving this equation in the red box. And we'll continue with that in a minute.